Why?
That would be like something that you can copy with.
No. Well, I'm recording now. I can say it again.
You can do it the same way.
Huh?
I bet you can't say it the same way.
I definitely can. I have range.
Range of what?
Like voice range.
No, you just sing low, you said.
Well, did that sound like a low saying when I was imitating her?
Yep.
Plus, I can imitate Meatwad from Aqua Teen Hunger Force. You like that show? Master Shake said I can go in the poo because I get dissolved and get caught up in the filter. I ain't never gonna get a 10 speed. Years ago, when that show was still popular, I had my students convinced that I was the voice of Meatwad. We're just gonna make ourselves a hot dog smoothie. I don't think so. See, look, they're talking in Portuguese. They're debugging scheme in Portuguese. I think I heard a 0 in there. All right, so let's do something. What was the homework? Are we on chapter 3?
No.
Really?
Well, yes.
Did I assign chapter 3?
Yeah. Yes.
So you had to read chapter 3.
Sorry, I get confused because it says part 2.
It's part D. Part D. Have you ever seen those Hot Shots movies? Hot Shots Part D. Isn't that like French? I think French for 2 is D. Do. All right, so this is what happens when I get a migraine. So we're gonna see if we can. What's up?
I was just going to say, speaking of French, I was looking for international travel today.
Oh, I thought you were gonna say French toast. All right, so we went. So we're gonna write all the processor crap from this thing because we gotta power through because next week is supposed to be C to assembly, right?
Mm-hmm.
So we're writing a compiler next week.
Mm-hmm.
So this week we gotta finish writing our processor, then we're gonna write a compiler for the processor. It's gonna be awesome. All right, focus. All right. So we already wrote branch of equals, so we're writing branch of not equal, and we're writing jump, and then set on less than?
Yeah.
All right. What program do we use? We use this one? And then Did I save our code somewhere?
On Slack?
It seems like that's something I should have probably saved. Oh, here. Oopsie.
Is Jordan coming today or no?
No, I think she's not feeling well either.
So you're not feeling well. Alexis isn't feeling well. Jordan isn't feeling well.
Yeah, so that's why we do this, so I feel better.
Because we're on vacation.
We're on vacation, der.
Ani. We're just gonna start dropping like flies.
All right, so let's review what we talked about last time so I could remember what we did. All right, so we have a program defined here called MyProg. We have a bunch of crap in here, so I'm adding the base of the 0 register and 5, storing the result in T1. So that's kind of like how we start an initial variable. We actually should kind of remember this because this is going to be part of our compiler logic for next class. Like how do you, like if you have a variable you define like int a is equal to 5, you have to start off by effectively getting a memory address for that variable a, then getting a base value of 5 into that by adding onto that guy at that address a 0 plus the value you're starting with. So you think about one of the weaknesses, or it's not really a weakness because processes are kind of a bunch of primitives, but one of the quirks of working with CPUs and working with assembly language is that it actually seems way harder to just get just a flat value into a register. Like, how do you get to a starting point? We accomplish that through the ALU by using an add instruction, just to say, that's why that 0 register that always has a 0 value is actually pretty important. That we just have this dude that's equal to 0, because we kind of need that as a starting point so we can call add to get base values into our registers to start doing stuff. All right, so this effectively adds or puts a 5 in T1 and T2. This branches if those guys are equal to test 1, which should then skip this line here. Remember last time we created that program counter, so when we are feeding off of our program, our CPU always executes the line that is next, that is at bucket program counter. We think of this dude as kind of like an array of instructions, or in this case, it's a list of instructions. This would be instruction 0, 1, 2, 3, 4, so on and so forth. All right, so what would happen here is inside of branch of equals, let's go and look, because that's what we wrote at the end of class last time, right? That guy should go through, look at T1 and T2, ask the question, are these guys equal to each other? If they are equal to each other, then it has to update the program counter. So it's going to have to go and look up and say, where is the location of test 1? That is, find me the line in my list of programs where the car is equal to the label I'm looking for. Once you have that line, then what are we going to do with it? We're going to update our program counter to be that line, so that the next time our CPU executes an instruction, it grabs the instruction at bucket program counter. So it's program counter that actually changed. We didn't somehow magically branch to this line. All we did is when this instruction was executed, we updated a variable, we updated an integer. That then the next time our CPU cycled, it said, what's my next instruction? My next instruction, as the program counter told me, is this guy right here. So we should see that, I think, if we look up a branch of equals. So we get the register value for the first register. We get the register value for the second register, if those guys are equal to each other. So that's that right there. If that boils down to true, then we wrote this function called MIPS find label, and that dude's job is to go into the program and find the instruction whose car is equal to the label that we are supposed to branch to when this is true, when it's equal. Make sense? All right. Once we find that, so this guy's going to get us so when we say MIPS find label, this is going to boil down to what this guy actually do, he will actually update the program counter. So he's going to update the program counter for us. So if I go to MIPS find label, is that up right above it? MIPS find label, this guy is going to take our program, he's going to take the label we're looking for, and we gave it a base place to start looking at bucket 0. Okay, then we started going through there and we looked at the car of the program, because remember we have a list of list instructions. So I'm going to get the car as a list, the car of that guy is my label. If the label we're looking for is found there, then I got my place. We will go ahead and update our program counter. So this guy is like a global variable that our CPU knows about. We'll update that program counter to be our position where we found that label, because that's where I want to start executing my code next. Otherwise, we call MIPS find label, passing it all the instructions except the first one that we just looked at. So the rest of the instructions, the same label we're looking for, and we're going to check the next bucket. All right, so the result of MIPS find label will be to update the program register. That's what that dude does. So back down here, if they're equal, update the program register. That's its job. Else, what are we going to do? We're going to increment our program register by 1. Because the next dude we're supposed to execute is the very next line. Make sense? Okay. And then we had this else in here for execute an instruction. I kind of vaguely remember we had a bug before because if we fail all of these, so let's say the next time through, we have our instruction that starts with, if it doesn't match up any of those guys, because when we're looking at our program, we're looking and saying, oh, is it that guy? Is that the instruction? Is that the instruction? Is that the instruction? Well, that's not one of our instructions. So if it's not one of our instructions, I must be looking at a line that's a label, correct? And if I'm looking at a line that's a label, what do? I execute the instruction of everything except that label. Make sense? All right, so we're supposed to do branch if not equal. So I can just steal this guy. And is it BNE? Yeah. Okay. I'll update it like that. Not equal. The same thing we had before. If that's true, do this crap, otherwise do this crap. So that's branch if not equal. All right, we can test it real quick. So we'll do a branch if not equal. So right now they are equal. So the next thing we should do is we should have a T3 is a 10 because it's going to do the next line. So if we see T3 is 10, then we know we did not branch. If I change this guy to a 6, we should not have a T3 as a 10, and instead T4. Well, T4 is always going to be, actually in this case it'll be 36 because I changed the value of T1. So T3 should still be 0, and T4 should be 31. T3 is still 0. I said 31, but 30 plus 6 is 36. So this is the correct answer. I am getting old. It's terrible. All right. Okay. So questions on branch if not equals?
Can you go back to where you put them at again?
Nope. Here. And it's possible there's an instruction like this. That might exist.
No, it's not.
Does it? So I just took the exact thing we had before and I just wrapped it in the function not.
And you...
That's all they changed.
Yeah, I see that. I'm trying to figure out where the...
Right here. That's the closing one for it. This is the opening one for it.
Random question?
Mm-hmm.
I somehow managed to get 2 screens of code and 2 screens of like the whatever you call it. Do you know how to?
Like this? You have like 2 of these?
Yeah, and then 2 of the bottom thing too.
But they're right next to each other? Like it's not
They're
like
on
tabs
top
like
of
this?
No, they're on top of each other, and so like I made one of each as well as I could, but it's still kind of annoying.
I'm guessing did you screw with like under window?
No, I did like Control D or something, or Control something. And
Well, is your code saved?
yeah.
Why don't you just close all of them and then reopen it? And then there's this thing called bring frame to front. So I'm guessing it's something in the window thing.
Okay, well, that worked.
So you're back in business? All right, so questions on branch if not equal? All right. What's the next one? Forgot.
Jump.
Oh, just jump. So jump. It's going to be this. EQ question mark car instruction. It's just J, like that. So if we're supposed to jump, then we're going to, so the car of the instruction, if that's J, the catter of the instruction will be our label. Yeah. So if we're supposed to jump, jump has just two things, the J and where we're going. It's not a condition, this is a unconditional jump, unconditional branch. So we will say, hey, if I'm looking at that, what am I going to do? I'm going to update my program counter. Where am I updating it to? The label I found in the catter of instruction. All right, so that's jump. And we should be able to test that real quick. Here, we'll cheat it. Make this a 5, and then I'll add another instruction. And we'll just jump to test 1 anyways. All right, so both of these are 5. Branch, if not equals, fails because it is not true that 5 is not equal to 5. So we continue on, but then here's our unconditional branch. We jump to test 1. Test 1 will skip this line and take us right to here. So we'll see T3 is still 0 when this is done, and T4 is 35. See, I mathed better that time. There's my T3 is 0. There's my T4 is 35. Hercules. All right, so. All right, what's next? Okay, that's what that sets a register if it's less than. How does that work? All right.
How you pronounce it?
Set if less than.
Okay.
Oh, I think I made. What is that? Well, is that a Chinese joke? You asked me how to pronounce that. I don't know if I can pronounce that.
No.
I don't think I want to try to pronounce that. See, Ani just got it.
If you say, I just say I don't know you.
Okay.
At least it's not my business.
All right. So, what are we doing here? So how does this guy work? Instruction sets a register to 1 if the value held in the register is less than the value held in another register. So this sets T2 to 1 if this guy is less than this guy. Is that what it does? This is T2. All right, so if T5 after the instruction below, so we're going to set T5, so T0, T2, T0 is a 40, T2 is a 55. It is true that 40 is less than 55, so that should be a 1. All right, yeah, I get it how it works. All right, so here, since right now our code doesn't do anything to T3, I got a nice blank slate with T3. I'll go ahead and we're going to SLT T3, and we will say, well, we'll say T1, comma T2, like that. So this should set T3 equal to a 1 if this guy is less than this guy, and a 0 otherwise. Only if it's less than, not less than or equal to, less than. Make sense? All right, so as this code currently stands, 5 and 5 are the same value. So 5 less than 5 is false. T3, oh, that's actually going to be a terrible test. So we're going to set this down to a 4. Here, I'm just going to set, we're going to do a T5 on this guy. That way I don't have to screw around with this other stuff. All right, so T1 is a 4, T5 is a 5. We branch if they're not equal, so we will branch. We won't actually do our jump here, but we're jumping there anyways. So now we're sitting right here because it is true they're not equal to each other. We're going to add T1 and 30, which is going to put a 34 inside of T4. And then we're going to set T5 equal to 1 if T1 and T2, if T1 is less than T2 and 0 otherwise. All right, so we're going to look at T5, and this current code is T1 less than T2, 4 is less than 5, so we should set T5 equal to 1 in this case. That's what the output should be. Let's go write the function real quick. So we'll put this right here, because that's the end there, right? Yeah. So EQ car instruction. Let's see, what am I looking for? SLT? That guy. And if that's the case, then we're going to ask the question if I need to get the value from a register. So we're going to say if less than whatever value is in get reg value. Now my instruction looks like this. So this is the, so I want to get this guy right here. So this is the car of the CADDR, C-A-D-D-R. C-A-D-D-R of instruction. And I want to compare that to the get reg value of the CADDDR of the instruction. If that's true, if it's true that the first guy is less than the second guy, then I'm going to set a register value. All right, so I'm going to, is it just set reg value like this?
Yeah.
And then I give it the name of the register and the value?
Yeah.
The name of my register is the CADR of instruction, and the value is going to be 1. Otherwise, I will set the register value
0.
to 0.
And closing.
Ninja. All right, so that should be SLT. Oh, it works. We don't have to test it.
Who knows? All right.
All right. Hold on. Where am I?
Not testing it.
I was legitimately asking the question, where am I in the world right now? All right, so T5 should be equal to, in this case, a 1, right? After we run this guy. Let's see, where did I screw up? So that should get me a register value. That should get me a register value. This should tell me whether they're less than each other.
Real. So
Are you sure this is specs? Yeah, so these guys, I might have given it the wrong number of D's there. So this is the car. This is the car of the CADDR. Oh, hold on. No, my code is written correctly.
Here you mean
My assembly language that I wrote here is improperly written assembly. Now it works. So there's our T5 as 1.
Yep.
And if I switch this guy back to anything other than anything greater than or equal to, it should now be a 0 in T5, which actually is not going to be anything impressive because it started off as 0, but we see that it's still 0. I promise I overwrote the 0 with another 0. Okay, questions about that one? All right, so Karan, you're in charge of making sure I don't write poor assembly code here. All right, everybody else is in charge of the scheme. You're in charge of this part. this part. If you see a comma, scream. We don't do commas in here. I'm just feeling that it's going to get twitchy, that comma button over there. All right, what's next on the homework?
Read the chapter 3.
Oh, that's all the programming?
Yeah.
Oh.
Keep it real over here, yes.
Well, okay, so then how long did we spend on this assignment? Give me some feedback. Huh? 3 hours?
Yeah. Yep. And I've rewatched the last part of the lecture. Yeah, I did too. As part of those 3 hours.
And how much time?
1 hour.
1 hour, so it's too easy.
No, I didn't say that. Just with the coding, not reviewing everything.
All right. So this was a reasonable amount of work?
Yeah.
Yes.
That was.
Did it feel like the right amount of work? Or could you have handled a little more?
No, because then we had time to start assembly. I did not have time to start assembly before.
Okay, so you felt like you were able to focus more on doing the chapter exercises.
Correct. Yes.
Okay. So that if I want stuff programmed, we should do it in class as a group. That's what you're saying.
Yeah. Hopefully, yes.
All right. Because we need to have a scheme. We're going to publish this. We're going to have a MIPS processor written in scheme when we're done. And we're going to put all our names on it. Because we wrote it as a team. Go on.
That could get someone an interview, right? Yeah.
I think it would. If you put on your resume that you once wrote a MIPS processor in scheme.
I hope I don't have to prove it.
just a right along.
We went to. Were any of you at the Battle Hack in Raleigh, Durham? Were you at the Battle Hack? You were at the Battle Hack in Raleigh, Durham. Man, I zoned there. It was awesome. Instead of 24 hours straight, wrote a programming language. 24 hours from scratch. It was awesome. Even supported recursion.
That's ridiculous.
I know.
Patient in what?
It was a JSON-based language. The syntax was all JSON. But you could write full functioning programs for procedures. That was a good day. That was the last time I was able to stay up for 24 hours. I don't think it's happened since then.
Yeah, the next time.
Because I had to go sleep in the car
Yeah.
when they were.
We were sleeping in the car.
Because I wasn't going to be able to. All the other guys had to like drive back.
So we drive a full day there, and then we had 24 hours of programming.
Yeah.
And we drive back.
Well, I didn't. I flew there. And then I wrote a programming language, and then I flew back.
Yeah.
All right. So let's see what's next here. There's some other good stuff in chapter 2, isn't it? Oh yeah, there's I/O stuff, isn't
Yeah,
there?
there's a ton of stuff. Like we could do like the rough so like half of the semester all the way.
No. We're getting this done tonight. This is happening tonight, or maybe a little bit.
Chapter 3.
Well, maybe a little bit next time. But next week, we're working on compiler stuff. Right? Yeah. So input, output in MIPS. This guy, let's see. To output an integer, a program writes the integer to memory location 8200. Special hardware detects a write to location 8200 and automatically outputs that integer to a screen. Let's see. So we can certainly write the code. So like if we look at this assembly down here, they are loading into T0 memory address 8200. That's what they're doing. So effectively what MIPS does is it says, we're going to treat 8200 as a very special location in memory. Okay? So nobody else should be using that spot in memory. It's a very special location. So we're going to load the memory address of that guy into T0. Then we're going to load into T1 the number 2, this constant, which I assume is what they're going to print here in a second. Then we're putting a 1 into T2, whatever. Then we're going to store whatever's in T2, which is a 1, at memory location 8200. All right, so this is going to put a, well, this should output to the screen a 1. So the second we store something to 8200, that should, this updates the store, the SW instruction. We already have an SW instruction, right? So now our SW instruction got a little bit more complicated because SW now needs to say, okay, you're storing something, but is the place you're telling me to put it, is that 8200? If it is, you're not actually asking me to just store it there. You're actually asking me to print it. In fact, I actually wondered, does it actually even store it?
It'll store.
Yeah, it looks like it does end up storing it there.
Yeah.
But we will print it to the screen. And I think, is it print or is it display for Scheme? Display? All right, so let's make output work. It's display. So just nailed it. All right. Display, LOL, except it needs to be like this. All right, so we'll go back up to our code here. So in order to do output, whenever SW, our store word, gets called, that was something we wrote, a couple classes ago. That was part of the really easy assignment.
No, super.
So good. All right, so this guy in here, this is the body of store word, right? And we can store that word there, but we need to do something a little extra, okay? Because we are ultimately storing it. All the stuff that used to happen should still happen, but we are storing, so we have an SW function, and this is the location, and this is the value. Is that right? So when we're storing something, we're always storing to a memory location. So we need to ask a question here. So I guess we can do this. Let me look. What does SW ultimately return? Where is SW? There we go. All right, so this guy takes in a register name, the location. So it's storing from a register into a memory location. So we're interested in that second value there. And then we're going to set the DM value equal to that memory location. And what does set DM value ultimately boil down to? So this does a set bang on data memory. How do I want to do this? We ultimately need to ask the question somewhere, did you just store something into 82? I feel like, we can hide that logic in all sorts of places. We can put it inside of SW, or we can put it inside of set DM value, because DM value would always be dealing with data memory, right? So set DM value is right here, and this guy is just setting the data memory here.
Just at the beginning.
Well, yeah, we can do two things and then ask the question. So this always happens. All right. So we'll put a begin statement in here, and we'll ask the question if mem address, if equals, sorry, mem address, and do we take that in as a symbol, or do we take it in as a number?
It is a number. It is a number.
Number. So we can use a single equal sign. So if that guy's 8200, if that's true,
Oh, yeah.
Yeah, the memory address is
Huh?
always number.
we're always going to ask if it's 8200.
Why that number?
Because that is the special memory address that if we are getting ready to store something there, that's where we display it to memory. There's special hardware in the MIPS processor that just sits there and pays attention to memory address 8200. And as soon as something gets stored there, it says, he wants to do output. And he outputs it. So we're getting ready to set a data memory value here. As we're in the process of setting it, we're going to do a couple of things in this begin. We're going to ask the question, if we were supposed to do an 8200, then what are we going to boil down to? We're going to do a display new val. And will they let me, can I do an if without an else?
No. Put something.
I'll just do a false there. Then we're gonna get a weird false displayed to the screen.
That's true. Is there like a continue or something?
I don't know. Let's assume not, and let's work with just what we got, because that's more fun. We can do like a set. I can say set bang data memory is equal to data memory. So I'll just set that variable equal to itself. I think that'll give me no actual output. Let's make sure it gives me no output, otherwise I'm just wasting my time. Oh, it gives me a void? Come on.
That's then you truncate the void.
Yeah, but then I'm still gonna
Does
get,
it know what data memory is down there?
yeah, because it's a global variable. Yeah, data memory. So we really want to suppress output. Here, let's just look it up real quick. Scheme suppress output.
You could write a function that's called print data memory. And then just call that in your else.
Well, but we're printing it.
Oh, but you,
Yeah, we're only printing it in the if, not in the else.
isn't that opposite? You're only printing it in the else, not the if.
No. If we was memory address 8200, we're printing. This guy does what he's supposed to do.
Doesn't, oh, you're just trying,
This is the else.
so you're not trying to print there.
No. Let me figure out. We'll just make the behavior work first, then we'll figure out how do we make it look nicer. So we're saying if it's equal to 8200, we're going to display and then boil down to false. Regardless, we're going to set bang data memory to the updated value. That happens regardless.
Yeah, it will always do it.
We just might do some printing. All right, so with that, we should now be able to come down to our code. And we should be able, actually, we don't have an 8200 in our data memory right now, do we? Okay, we're gonna just, went a little out of order. We had some bad sectors. So we have an 8200 now. All right, so we have 8200. So now we'll go write the assembly. All right, remember, Cron, no commas. So this is going to be 8200 in T1. We'll do a 5 into T2. Get rid of these branch things. And we will store word into T1. Oh.
No. You're too slow.
T2, so we're putting a 5 into memory location T1, so this should display a 5 to the screen.
And false.
Oh, hold on, did I? Oh. There's that. There's that. Oh, yeah. I stole my opening parenthesis for the other thing.
Expecting a number as the first one.
Am I calling my SW wrong? Is this the right syntax for SW?
What are you trying to do there?
Go back and.
I'm trying to store my word. I'm trying to store into memory address T1 the value that's in T2. What does SW take?
Yeah, you should have already checked the.
Yeah, I think it's so.
All right, so here's my SW. I'm gonna pass it the catter and the CADDR, and that's what's going into SW. This one. That's taking in the register name and the memory location.
You should be using the get drag value.
Well, I already have it because we did this inside of set mem or set dm value. That's this guy right here, set dm value. We're asking the thing if mem address is equal to 8200. If that's a true statement, we're going to display that new value, which should already be resolved.
That is T1 in your parameter.
I think you should just switch it or something.
You should, in your command, you should using
It shouldn't be like
get value of SW, then get value of T1.
yeah, because the next one should be the memory address, right?
Oh, I don't know. Is that how it's written?
No, that you
How did we write the instruction?
T2 is
So you're gonna first like if you wanna test, you should do like a store T1.
Oh, so how does our SW work? Does our SW require us to give it an actual memory address, not a register that has a memory address in it?
yeah.
Correct.
If it is given
Okay.
to you,
So from
should be
T1.
I gotcha. So we're going to load, so what's the syntax? Is it
should be
the value, then the memory address, or is it the memory address and the value?
The memory address is gonna be the T1 then.
All right, so we would put in 8200 here.
Correct.
And there's our 5.
but it doesn't display. Where's the display?
Right here. I highlighted it. It just didn't kick it down the line.
There, you highlighted it.
Yeah.
It seems like dollar symbol.
Yeah, and it actually did not put that false out to the screen.
So
Oh, it wouldn't. It wouldn't. So if I do 5200 instead,
Yeah.
actually it wouldn't be there. That actually makes no
It doesn't
difference.
matter.
Now we'll get the false to the screen. Assume 5200 was one of my instructions, one of my memory locations.
But it doesn't yelling to you.
No, it's not. I'll just do 5000. 5200 wasn't one of them, so it would have not found it and not done anything.
Just skip that one.
So if I do 5000, now we should get the false. Oh, it doesn't print the false. So false is kind of like that special.
That's good.
Yeah, it seems like the false is the, hey, we think you mean not to do anything. All right, good. So then it works. But SW should work for,
It has a get value in the code. It has 0, then parentheses, the address, the
but we don't have a way of putting a memory address directly.
no. Unless you create one.
It seems like we should, oh, we can fix this real quick. I got this. We'll just ask the question. If that second value, if it's a number already, then it's a resolved memory address. If it's not, we'll go ahead and resolve it. So we'll just make our single instruction work both ways.
Okay.
So then up here inside of our SW, where's my SW? All right, so SW here is getting a mem location, and I'm gonna, before I set that value for the, actually, should I do it here or should I do it in the, let's do it in our actual code here. I think it'll make our kind of fake interpreter processor easier to read. Yeah. All right, so if we're looking at an SW, we don't necessarily want to just immediately assume that we can just call SW blank. We want to ask the question, if, and we're storing into, this is the memory address here, right? So if number, this guy, if that guy's a number, then we can go ahead and do that. He's a hard-coded memory address. We don't have to resolve anything. Otherwise, we have to call SW on the catter of instruction, and we need to go ahead and resolve the value. So we need to get reg value. The CDDR instruction, like that.
Okay, yeah.
Yeah. So we're just asking the question, what did you send me? You know, when you said store word, did you give me a literal memory location, or did you give me a register that has a memory location? If you gave me a literal memory location, I'll just use it. Otherwise, I'll go ahead and resolve the register to get the memory location. That make sense?
Yep.
So now we can come down here. So now putting 8200 into T1, I should now be able to do T2, T1, and now it should give me my 5. There's my 5.
Okay, not yet.
Wonder if, can you do after a display, can you kick it down a line? A carriage return?
Yes, it's slash something. I have some.
Just slash something?
I
Just put a slash or is it backslash n?
yeah. I probably backslash n. Let me get it.
I guess I could just do two displays, right?
So yeah, it's backslash n. Then you do two displays for that.
Two displays, yeah.
Yeah.
All right, so here's my display new value. Oh, so actually that kind of sucks. I wonder, can you give display more than one thing?
Yeah.
Oh, otherwise I have to do it to begin, but I'm going to map display across the list, new value, and backslash n.
Oh, you want to display multiple at the same time?
I think that'll kick it down the line.
Missing?
Oh, no, it's oh, wait. I want it to resolve the new value. Oh,
The thing thinks that image doesn't
yeah.
Maybe you need a double.
No, we're fine. We'll just build the list. List, new val, and backslash n. Oh, but it didn't resolve the new val. I got my T2. Yeah, it didn't even kick it down the line. Is this even the thing? Is this the thing?
Yeah.
Are you-
But you need to.
But
Hold on. You need to put between two. What is that?
Oh,
Quotes,
single
double
quotes like
quotes.
this.
Yeah, but double though. Double. Gotta make double quotes.
Yeah.
put a string. Really? I think. No, you just add in without.
Fine.
Right to the.
Scroll off your.
Oh.
What happens if you?
Oh, so this thing might have looked awesome for a while.
Yeah.
Or what? I'm leaving it now.
Let's go to work already.
All right. So there. Now it works for direct memory addresses or memory addresses stored inside of
Right.
registers, and we flag on 8200 to display something. All right, so that's output. But now we can do input too, right? Doesn't this thing support input? Yeah, we'll do input and then we'll take a break. How does input work? Can we read this? Does it tell me input? It's 8200. The computer system needs to accept user input. A program may accept user input, then output 2 times that input. Blah, blah, blah. Is available. 8196 to get the next input value. After checking 8192 is a 1. Okay, so 8196 has the input value, but we only check that if 8192 is equal to 1, which tells us that we just received user input. So we actually do it with 2 addresses. So the hardware detects that a load like that. So when we store a, let's see, the hardware detects such a load and automatically puts the next input value in 8196.
So how we can accept the input?
Yeah, how do we accept input?
What was in the sixth chapter?
Here, we're loading a word into T4 8196, or from loading word into T4 from 8196. 8196 is the actual value, but we only did that after we got something into 8192. Give me an example. Oh, here, get in. So this loads, this is keyboard ready, so loads T1. T1 is 8192. It puts a 0 into 8192. Then if 8192 is equal to a 0, because we're looking off of T3, so we're loading a word T3, whatever's in T1, which is 8192. 8192 tells us whether or not to load a value. So this guy is saying keyboard ready, so basically we reset whether a value should be read in yet. So that's why we set this to a 0. So the very first time through, 8192 is going to start off as being, this guy right here is going to start off being equal to whatever T3 has in it, which is 81, well, let's see. We're putting in T1, 8192. Then we're loading a word into T3 from T1. So we're getting the value at memory address 8192. And 8192, this memory address, it didn't actually start off at a, it started off as at a 0, I would presume. So it starts off at a 0. We load the value into T1. Keyboard's effectively ready because when this guy is a 1, that means the keyboard is reading input in. So then we add into T2, 0 plus whatever is in 8196. Oh, no, because this guy's giving, this isn't starting off with base memory. This is starting off with this thing being at a starting point. So they're actually saying 8192 is already a 1 somehow. Somebody already set it to a 1. Therefore, the next thing you should do is find that in 8196 is your value. Okay, so now we're asking the question, is T3, which was loaded from T1, is that equal to a 0? Well, T3 came from 8192. 8192 is a 1. Is 1 and 0 the same value?
No.
It's not. So, and what do we do if it was? We go to done, which is the very end. So since it was not a 0, which means that we do have something to read in, then we'll put into T2 a 0 plus whatever is in 8196, which is the contents of the input, however it got there. Make sense? So this is like a little function for doing input output, which I'm guessing is from the next chapter. Next chapter probably has what, like subroutines in it, stuff like that. So yeah, and this just multiplies it by 2 or adds it to itself. Yeah, so this is a little function that doubles it. So for us, what we need to do is whenever we check? Whenever we see a 1 in 8192, we should read the value from 8196. But this would kind of be like a hack for us to make this work, because for our code, we'd actually have to load the inputted value into 8196 first. Then we'd have to set 8192 and say, read from 8196. It would automatically read from 8196 and then do something with it. Let's see if we have a way we can, no, so they really gave us kind of a halvesy 8192 thing. Well, we can fix that. How do we read stuff in with scheme? Scheme input. The scheme read from user. Simple input in scheme. Oh, it's just called read line.
Read line.
See how that works. All right, so read line asks, this was it. Read, oh, it was, did it just read? Oh, well, okay, we read it in. Oh, but where do we read that to? Define A to be 0, and then set bang A to be read LOL, print out A. Okay, so I can do a set bang on it. So we need to invent an instruction for input in our thing, which will then ask for user input, read that in, store the result into, and we're only going to support numbers, store the result into 8196 after setting 8192 equal to a 1. All right. Oh, and then we can do a little let for this one then. What should we call that function? Just input? Yeah. I hope not. It's going to be in a list anyways. All right, so we'll do that. Then we'll say, so the name of our function will say input. So yeah, that guy is just going to be, read from keyboard. All right, it's going to be awesome. Yeah, we do need to make sure that this does prevent us from having a label called input though, because this guy will look like a label on our else.
We should have equal to, equal to.
So EQ, oh, Ninja. EQ car of instruction and input. So if we're equal to input, then we need to do a couple of things. The first thing we're going to do is we're going to call SW and pass this guy a memory address and a value. So we're going to pass it a 1 and an 8192. Is that the...
It is checking whether 8192 is 1.
Yeah, but I have to set it first. Yeah, so if we go back to this, see how it actually functions. When I go to read something in, if I want to input something, we have to set 8192 to a 1.
Yeah, you have to set it to be 1.
Which then will make the value get put into 8196. So 8192 will get set to 1. We'll read in our value, store the value in 8196, and then set 8192 back to 0. It's been read in. So ultimately, I don't actually need to set it, but we should mechanically set it so we see how it works. Because we're saying we're reading something in, 8192 is a 1. Read it in, put it into 8196. Then set this back to a 0. Done reading it. And 8196 can stay whatever it is. So SW takes in a value and a location to store it.
Yeah.
All right, so if we're doing input, then we're going to do a begin. The first part of this begin will be that guy. We'll do that. Then we're going to store word what value, the value that's returned by read, into 8196. Then we'll store word 0 into 8192. That's what we do for an input. So we need to add 8192 and 8196 to our data memory. Okay. And then our program down here will input. And what does input do? It's going to read in, so they set 8192 to 1, saying we're ready to read in.
Yeah.
Then actually read something in, putting the result in 8196. Then set 8192 back to a 0. We can say that mechanically we didn't need to do that since the end would be a 0 anyways, but that is actually what's occurring since we're having to fake the actual input flag, right? So we'll input something here, then we should be able to load word from, and we really actually do need to update LW as well to work for direct and indirect, but we're going to load into what, T1 from 8196. Something like that.
That's a little tricky. Because no matter how it's a number. So now does it load 8196 into that, or the value of memory address?
Oh, that's a good question.
You cannot use it if it's a number to check.
Yeah, so how do we say 8196 for load LW? I mean, it doesn't really matter here because we can see that our logic just worked just by doing input because we get a dump of our stuff at the end. So if I put a 4 here and press enter, looks too large for list. It got an index of 3. So this is what it got, is a list containing the list. Is that instruction not formatted correctly for how our MIPS CPU works? Or we take a program, as long as we have at least one thing in the program counter, we create a list out of a register file in our data memory. We begin, we execute instruction, we call get instruction on our program, which should load bucket 0. Then we call MIPS CPU on the program. So MIPS get instruction is what we're going to execute.
Zero, right? You missing a 0?
Well, can't we have an instruction that just has one thing in it? Or is that not allowed? We have to have
Yeah.
Huh?
Is that what it's yelling at?
Yeah, it's yelling that I don't have enough things in my,
You have to have two.
What if
You the
it's too large for list because it's looking for index 3.
so doesn't it understand that needs to be the name of the function and two more things happening after that?
That seems to be the assumption we wrote. So we always have to have at least 2 things.
Yeah, that's what I thought.
No.
No, that is not the default.
Well, we'll actually know pretty quick here if we just put the third one, because that, so add I would take 3 things always. Okay, so that's not the problem. Just real quick, I want to make sure input is not an instruction. Okay, function's not defined, that's good. So we call MIPS CPU on my program, we give it input MIPS CPU, it takes a list containing exactly 1 instruction. Program counter, we default to 0 when the thing first starts. We create a list of our register file and our data file. Oh, no. So if this is true, that means we're done with our program, so we output our register and data file just so we can see the contents of it. Otherwise, we're going to begin doing something. What are we going to do? We're going to execute instruction, MIPS get instruction on our program. So our program initially should look like this. It's a list containing exactly 1 element, which just says input as an instruction. Okay, so what does get instruction on that guy do? MIPS get instruction takes in a program. He gets list ref. And so this is what it's complaining about. So list ref of program, index too large for list. The index is 3. Why is the program counter set to 3? Oh. No, it's getting set to 3 because I'm doing 3 things. Storing a word. Well, no wonder it's getting set to 3. Because it is asking me for the input. So it's doing, where's my logic? 1, 2, 3.
All right.
So really, I only want to do 1 thing. Because I remember I said that this is kind of like, actually, it's setting it to a 1 and then back to a 0 after we do this middle thing.
Mm-hmm.
So I guess we could kind of do set bang program instruction equal to minus program what is it called? Instruction counter? What's it called? Yeah, program counter. So we'll cheat here. So program counter equal to minus program counter 2. And that'll be a set bang. And then to get this guy to not actually display anything, we will create a list out of a false and that, and then return the car of the list. So this set bang thing here is the guy that gives us the void.
Yeah.
So he'll update program counter, but ultimately give us a void. Then I'm creating a list out of false and that void, and then I'm boiling it down to the car of that list, and we've seen that false gets not printed.
I see. I suddenly realized what's going on.
I'm missing a closing.
I was gonna say I have 6 and you had 5. At the what you just wrote.
Oh, yeah. $81.96 Where's my?
Why is not asking you
Oh,
for
they
the
actually set two false.
and we have other false things.
This was my read.
Store one, store three.
Oh, SW, is the memory address second or is the memory address first?
Memory address should be the second.
Okay, so this is what I'm storing in this location. So I'll read in something, which we're doing, and then we're storing, I read in like a 4. I'm trying to store a 4 in 8196.
It should be like the memory address first.
That's why I just asked. What does SW take?
Check the parameter, check the declaration again.
Oh, that was it?
Be the memory address second.
Yeah, register name and then the memory address.
Okay.
Oh, but this guy's trying to get the register value. That's why it's getting the false. So I actually need to put it into a register value.
You should read the.
Yeah, so this guy, I need to put this into a register.
Yeah, then put the.
Then give the register name.
Yeah.
So I'm actually going to.
Add.
That's like the thing when I entered in a 4 when I first run this.
It's listening.
Yeah, it's listening from scheme. So I actually need to put that somewhere.
Yeah, you can use add. It's fine.
Or we just make store word work for. Oh, store word always needs a register.
Yeah. So it's always reading from register.
So that's fine.
to-
That's fine. So then we won't actually do these as stores, which then will mean that we don't actually have to update our program counter. So this will be better anyways. So rather than these being stores, what we'll do is we'll directly write to memory. Instead of get to memory through a store instruction, we'll just write to 8192. We'll write to 8196. So that is what, set DM?
Set DM value.
This guy takes a memory address and a value. So we will just call this guy 3 times, which actually won't update the program counter at all. So we would actually, in this case, actually have to implement the increment the program counter ourselves. So rather than subtract 2, we're going to be adding 1. So this should work. What am I doing? Where am I at? Ninja. All right, so we are going to set DM value
The
8192
we,
to 1,
oh,
right? Gotta give it the memory address. Isn't that what it was? Yeah, memory address, then value. All right, so I'll set 8192 to 1. Then we'll set DM value 8196 to read. Then we'll set DM value 8192 back to 0. And then we'll do our car of the list of false and set bang program counter equal to plus program counter 1. Here, I'll kick this down the line so it's a little more readable. So that's what we do in that begin. If it's equal to input, we'll directly set memory 8192 to 1. We'll directly set memory 8196 into whatever we read in. We'll directly update 8192 to 0. Then we'll update our program counter ourselves. Yeah. And we could have, yeah, we'll leave it like that. Instead of doing this weird thing here, we could have done the set word directly for this last one. So we could have said SW 0 that and let him do this program counter thing for us. This is actually equivalent. We'll test this real quick, but inside of SW, we increment the program counter by 1. So directly set memory here, which doesn't change program counter. Directly set memory here, which doesn't change program counter. Then update memory through a store word, which does update oh, I'm missing my whatchamacallit. Yeah, the same one as before. Oh, same problem we just had before. We do need that other line because our SW doesn't allow me. I have to pass it a register. I can't pass it a hard-coded value unless we fix it.
So what is this? What's going on with this SW there? That has the 0 in the.
Yeah, I'll explain what I'm trying to do there, and then what we would have to do to fix it.
SW has the updating the program counter inside.
Right,
Yeah.
but it's looking for a.
This guy right here, that guy right there, is attempting to do the identical thing to what this guy does,
Okay.
but he comes with a program counter increment.
Mm-hmm.
So SW has program counter increment built into it.
Yeah.
But what I could actually do is I could say 0 register.
Okay.
So this would actually be a pretty accurate
Okay,
representation
yeah.
of
You
CPU.
counted the values from there.
I'm updating this memory location to the register 0.
Okay.
Okay, so this directly sets memory 8192 to a 1. Does not modify program counter at all. I'm bypassing all that stuff. I am manipulating memory directly. This is how we do a read-in scheme, but I'm taking that value and I'm directly manipulating memory. Does not impact program counter. As far as the program counter goes, I have not actually done anything yet. Then I finally do something by actually doing the SW instruction, putting whatever's in register 0, which is a 0, into 8192, kind of letting us know that input is complete.
So now then it can understand that if you just leave 0 there.
You
it's
you
not
need
So the-
reverse.
single quote,
That guy.
otherwise it's a variable. Hey.
It is called 0, isn't it?
Yes.
My register?
Yes.
Go to the top 320.
Yeah, I saw it up there. You say what? That's pretty funny. It's input, do this, do this. SW takes the name of a register and a memory location. Is that correct? Not a memory location followed by a register?
that.
Register name
You are
and a
right.
memory location.
You are right.
It's going to set that memory location, second guy, equal to the get register value of reg name.
Which line breaks it?
We'll look at this more closely.
Apparently, it is after this SW, like you said, DM value.
Yeah, possibly. So let's look at it closer now. I'm going to try to put a 4. The ideal situation here is that 4 is actually at the end of 81, or is in 8196.
Yeah. Oh, here. It's here.
So does SW not actually update the program counter?
Oh,
your-
you are
your
the
instruction
pro-
is.
If you
is
set to
affecting the
1,
parameters.
it's exceeding the list. So after you set SW, now the program counter is 1,
Correct.
and you are looking for 1, and then it's
But I'm not looking for 1. This is the code I just did. I'm not in that else. This would have been the next time through. So the next time through is from down here, where we said, go and get me the instruction if the length of the program is greater than the program counter. So that must mean that program counter, the length is 1. Program counter's not updating.
Yeah, I was gonna say, where are you incrementing it?
I was assuming it increments in SW.
Well, we're not changing the program counter at all in there.
We're not doing it in the thing there, but are we doing it in SW?
That's what I'm saying. I don't think that
SW.
Well, actually, let's just check real quick here in the our code down here where we actually call SW. And if we see him updating the program counter, we'll know real quick that that's the problem. All right, so this guy, so he doesn't do anything here. SW oh, he doesn't update the program counter either.
So it's in the set DM value.
We were doing it in the extra.
Oh, I see, said the blind man.
Cause for what we were doing, it ended up working better that way.
Yeah, here's our set program counter. Yeah, so we we're going to. This is like 1 parenthesis or something from working. So you set, well, it's not even that. It's not even that. It's our program counter is just not updating.
You are checking the B equal. B equal.
Well, we're doing it there. We're updating our program counter, but where are we updating our program counter and all the other ones?
This is we.
We're not.
If we check the code.
So we're only ever updating program counters when we did the branching because we just didn't worry about it for the stores and stuff. Okay. So then let's take a break. We'll come back. We'll fix our program counters for all of our normal things so that our branching works now, but had we done some storing before our branching, it wouldn't have worked because our program counter would have been off. It was because we were just testing branching last time, not testing branching with storing. We were just putting things directly into registers. So we just need to fix store and load for program counter, and then we'll be back in business.